Then God said, "Let there be light," and there was light. This ancient description of the creation of the universe found in the book of Genesis may be accurate after all. The Big Bang Theory describes the beginning of the universe as having been precipitated from an infinitesimally small point. In this small volume, all matter and energy was concentrated until its contents exploded in either a smooth expansion or an incredibly violent energetic explosion that formed the planets, stars and galaxies. Originally this theory had competition from what is called the steady-state theory, whereby the universe is forever expanding and new matter and energy is created spontaneously within the space left by the receding galaxies. However, empirical observations have directed astronomers and scientists into the acceptance of the Big Bang model. But how did we get to this point in our understanding? In the early part of the 20th century, the American astronomer Vesto Slipher and the German Karl Wirtz made some important astronomical discoveries. Using spectral analysis, Slipher deciphered the mixtures of gases contained in planetary atmospheres as well as nebulae. What distinguishes his findings is the discovery that most if not all galaxies outside of our own demonstrate what is called a redshift. This shift is simply a change in the wavelength of the light emitted by those objects under investigation towards a longer wavelength. Wirtz similarly catalogued many redshifts of the nebulae which he chose to study. But it was still too early for them to realize the full potential meaning of their observations. That would wait until Einstein's general relativity would be interpreted by other scientists through further mathematical analysis. His contemporaries demonstrated to Einstein that his new theory of general relativity published in 1916 was not compatible with a static universe of space-time. The theory predicted an expanding or collapsing universe but not a fixed cosmos. Because he personally believed the universe to be an invariable space-time continuum, Einstein engaged in a degree of scientific legerdemain. To correct what he perceived to be as flaws in his theory, he added the contrivance of a cosmological constant known as lambda to force the static universe into reality. Einstein's view of perfection in an unchanging space-time continuum had led him down a blind alley as much as Aristotle's concept of perfection had brought that great philosopher into the error of believing in a static Earth at the center of the universe. But even with the addition of the cosmological constant lambda, the universe was still found to be unstable, and this whole affair would later be viewed by Einstein as his greatest blunder. His cosmological acrobatics behind him, Einstein yielded the stage to others for a clearer understanding of his own theory. It fell to Alexander Alexandrovich Friedmann to consider the consequences of general relativity without the constant lambda interfering with his study of these relationships. In doing so, the Russian mathematician and cosmologist derived the solution which predicts an ever-expanding cosmological structure, 1922, a prediction which was disagreeable with Einstein's concept of universal perfection. A couple of years later, Friedmann published his findings in About the Possibility of a World with Constant Negative Curvature of Space. But the entire hypothetical construct still lacked a complete verbalization mathematically and theoretically. Enter the relevant Father Georges Lemaître, a Catholic priest from Belgium. Reverend Father Lemaître provided the equations necessary to formulate the basis of Big Bang theory in his work entitled Hypothesis of the Primeval Atom. He postulated that the universe began as a primordial atom of infinitesimal volume and enormous mass energy, as well as space and time and everything else comprising the future universe. At some point the universe began with the explosion of this superatom. Lemaître published his theoretical ideas between the years 1927 and 1933 and speculated that the movement of the nebulae demonstrated the validity of the explosion of his cosmic superatom. Unfortunately, he also wrongly believed that cosmic rays might be an after-effect of the superatom's Big Bang. These are now known to be generated not from the universal conflagration but from galactic sources unrelated to the Big Bang. However, the new theory still lacked a major source of observational support. This would be provided by Edwin Hubble's observations of the redshift of galaxies. Taking up where Slipher and Wirtz left off, Hubble employed a novel technique to discern the properties of the galactic movements. By choosing to observe stars that are known as Cepheid variables, he could more accurately make measurements. Cepheus are a type of star that brighten and darken and lighten back up in regular periods of time that are well known. Cepheus that have identical cycle times of brightening, darkening and brightening again also have identical or nearly identical luminosity. Thus, if one compares the length of the cycle to the amount of light apparent to the observer, it is possible to accurately prepare an estimate of the distance to the Cepheid. In this manner, Hubble had found that the nebulae or galaxies exhibited a galactic redshift, in other words, that galaxies were receding away from ours at a speed which is correlated directly with the distance between our vantage point and the galaxy being studied. The further away the galaxies were, the faster they appeared to be going and moving away from us. The results of these investigations is now known as Hubble's law. Essentially, this law states that universe is in an ever-expanding mode whereby the intergalactic distances continue to grow without bound into infinity. Hubble's law depends upon the shifting of the wavelength of light, and after having been delineated in 1929 has been subsequently proven over and over again. Further, Hubble's constant has been recalculated to a more perfect value and retains a great probability of being recomputed in the future based upon new observations. Thus, it should be clear to the reader that our scientists have a fateful habit of introducing their preconceived notions of beauty into their models. From Aristotle's static Earth to Einstein's greatest blunder, the constant which forces a static universe, we proceed only from the wisdom of our weak minds. The more things change, the more things stay the same. Man's hubris knows no limits in our attempts to understand things without the wisdom to comprehend its underlying meaning. Humble we are not. We are making the same mistakes we always have. Back to the Future. To be continued. Author Bio. Michael Strauss is an engineer and author of Requiem for Relativity, The Collapse of Special Relativity, a serious critique on the fallacies of special relativity. To contact the author, visit www.relativitycollapse.com.